Hey guys, so we're going to dive into 5.2 talking about exponential functions, and the first one that we want to deal with here is looking at just the positive and the negative functions of both integers and then fractions. So with integers, we see that, think about your y-intercept being where x is 0. Well, we know that any number to the 0 power is really just 1. So we get that point right here where 0 or x is 0 and y is 1. Then when x is 1, we know anything of the first power is itself. So then y just becomes 2 when x is 1. Now beyond that, we start to get faster, we start to get y values that increase faster and faster and faster. So when x is 2, y is 4. When x is 3, y becomes 8, and it keeps going exponentially fast from there. Now conversely, over here when we have fractions, we start at a small value when my x is 0. So again, I'm at 1, but then I go to a half, and then a fourth, and then an eighth, and I keep getting smaller and smaller and smaller. And this gets into the problem of infinity, where it's never reachable. We'll get closer and closer and closer to 0, but we will never actually get there. But going the opposite direction, when my powers get negative, well, it flips this over before it applies the power, so you have to think it gets larger and larger and larger very fast, because when it flips over, it is essentially the positive direction of the 2x. And then you can see the negative graphs for each of them. Just flip them, they reflect over the x-axis. Alright, so now let's look at evaluating exponential functions. So an exponential function is described by having a piece where an exponent is the variable, the independent variable, that then determines the value of the function. So f of x is kind of a prettier way of saying our y equals. So now we have a function relative to the exponential x, where 20 rabbits triple every half season. So then x is how many half periods have happened, because our variable always has to be how many of something, how many cycles, how many periods, how many years. So how many rabbits will there be after 3 years? So if we start to graph this, not graph, but plug in values, so we determine our variable that we use, and if it's 3 years and x is a half year, then we're going to have 6 half years happen. So we'll have 20 times 3 to the 6th power, and that we need to evaluate to see how many rabbits there are. 3 to the 6th is 729, and that then, when fully simplified with the multiplication, gives you 14,580 rabbits. So you can see how populations can get out of hand if you don't do something to control them. Now when we look at graphing exponential functions, we want to put this on a graph where x and y are related, and these get kind of difficult to draw, especially on my SmartPad. So I am just going to drag this over. So what we would want to do is make a table. And you always want to start with some negative, go to 0, and some positive. So we're just going to sub that in for our variable x. So -2, -1. Remember, these negatives flip that and then apply the power. So since the 0.5 is not being applied by the power, it stays on top. So these are quite small values, and then we get larger and larger and larger as we go. So we get this nice curve that this essentially goes to a straight line. It's not quite. And this as well, off in the negative value, essentially goes to a straight line, just not quite. So again, for the got it on part 3, I'm just going to drag over this table, because this is exactly how we would solve it. Just set up a table of values, plugging in, but we can't zoom negative, so we would just start at 0 and go up by our integers and find our points as we go exponentially. So actually, then when we were asked to look at the percent change in zoom every time we zoom out in part A, it would actually be 300% change. So the first thing I want to explain to this problem is about growing by percentages. So this says that a museum is growing its visitors by 5% each year. So it's going to still sustain all the visitors that it previously had. So it'll still have 100% of what it previously did, but then it will have the 0.05 as well on top of that. So that's where we get this 1.05 is because it's growing by 5%. So when we set up this problem about the museum, you can again make a table, and especially if you have a graphing calculator that can help you out, or you can just plug this in, and every time you change this, then you can just multiply it by 7,500. But here's my table of values that I get, and y again is my visitors attending the museum. So I plot those points over here, and then I can be able to predict the attendance based off of that, and we could connect it if we wanted to be able to predict points between the years. So say after half a year, or 3/4 of a year, or anything like that. Just like in the Pearson example, the got it is not much different. When you have the total mass in grams of a culture in a petri dish represented by this function, what's the graph of that function? Well, we can graph the 2 times 2 to the x function, but then because of the plus 50, it will have a shift, and they are trying to trick you here, but it in fact is this graph that is shifted upward to start its y-intercept right at 50 plus 2 times, well, at 0, this would be 1, so that is actually at 52. I'm quite bad at drawing these on the computer, so we will talk more about these in class, but here, for the got it's of part 5, go ahead and pause the video and try these out on your own. So what we know about our functions here is that they're parabolic, and a parabolic function, just by its shape alone, will most often have 2 y values for any one x value. So here, our solution for a, if we put it in the graph, this would be the left side of the parabola as it goes up. And where does the y value equal 5? Well, that actually is right about negative 1.33677. It starts to kind of taper off after that, but that would be one of our values for that function. And I cannot actually figure a way to get the right side of this parabola to show, but if it did, you would see that the other x value for this solution is at right about 5. So our two solutions are negative 1.336 and right around 5. I completely misspoke there for a second. I had plugged something wrong into my calculator. These functions are still only exponential, not parabolic. We are not there yet. So this actually regresses closer and closer and closer into 0, so there is no other value. It's just that negative 1.366. My apologies for that. One of the fun things about the one shot and done with these videos. So go ahead and look at B on your own for a second. And then B, our two functions that we want to graph are both the left and the right side here. And I cannot actually get my emulator to work at the moment, but if you graph this, they're both, well, they both look like lines, although the one would actually be an exponential. And then where they cross at the x value. So when you zoom back out, you can actually see that, yes, the one is exponential, and our x value solution is negative 0.45203, and that is slightly rounded, but that is where the two lines cross, which would make their solution. That is all I have for exponential functions, so hopefully you will let me know if you have any issues, work through the Pearson modules, do your homework, and have a great day. Thank you very much.